Well, hi, DSA coder. So you're working through the algorithms for the binary search tree, and this video is just if you want to have a bit of a chat, bounce some ideas on the algorithms. So let's give that a shot. So binary search tree, setting up the algorithms for that, and I'm going to include the structure a little bit in the algorithms too. Strictly speaking, we might not do that, but we'll let it go here. We'll let that happen. So if we look at a tree, you've already looked through this stuff here, I'm sure. So if we look at a binary search tree, we see, first of all, if we're listing our objects, we definitely have a tree, right? We have one tree. And then, kind of like the linked list has a first and a last, well, the tree actually just has a root. That would be the root of the tree, right? And what are these things here? They look kind of familiar, right? Well, there's data there, but they're also node-like objects, right? So I propose that we would construct a node for these to help us out. So these would be nodes. And then what would that node look like? It would have data like our other nodes, and it probably would have a left and a right. You could call it something else if you wanted to, but I think that's pretty intuitive, left and right. So that would be our structure, our data structure. And then the things we want to do with this tree, basically two fundamental things. We want to add into the tree. We have to add elements in to build the tree, right? Initialize it. And then we want to search. That's the whole purpose of this tree is fast searches. So we want to search into it. So let's take a look at what we might think about for algorithms here. Again, like we talked about, with the tree itself really has just one fundamental child, and that's the root. And these two are more implementation details here. We have not two, so one is a sort function here, a sort function and a search function. But this is the fundamental thing we want to look at first here. The node itself, as we talked about there, it really looks to me like we would want to have the node, and then it would have data and a left and a right. And the left and the right would also be types of this node, right? They would be types of nodes. So there we go. The high-level algorithm for the search, we'll do search and add actually will work very, very similar as you can think about it. If we search, let's say for the 30, we find it and we return it. Well, the add is very similar. If we're going to add in an element, something like a 25, it would end up, we would find a position, the insertion position, and then add it in. So the key is finding that position for either the search or the insert. Let's take a look at search first, a little bit simpler. So the tree would have a method, a search method. This is a very high level algorithm here. Searching for 30, let's say. So now what I would propose is having the tree just delegate, just send the message to its child, the root. So it's going to send it to the node. So the node is really going to be where the bread and butter is, in my mind, for the algorithm I'm thinking about. So the node then would have a search method also, and it would do the comparison. However it does it, that's an implementation detail, but it would do the comparison, and that result is going to be less, match, or greater for that key. Is that key less than, or the others? If it's a match, if the key is a match, hey, we have the answer already. We return that data. If we don't have a match, we continue on. If it's less, then we would search into our left tree. We would continue to search to the left. Otherwise, we would search to the right. So what does the search left look like? If we didn't find a match, if we were searching for 30, let's say 30 doesn't match that 50, but it's less than, so we would do a search left. What would search left look like? Well, that was a very simple one. All it would look at is if left is null, we can't search left, right? So then we would return null. We didn't find a match. That would be a case where if we were looking for, let's say, searching for a 29 key or something, we would get here, it would be less. We would have left is null, so we would return null. Otherwise, it's not null, so we could simply pass that same method message, search left to the left side. And we continue that on actually. So in this case, searching for 30, we would be the left. Well, this time it's to the right, then to the left, and then a match, and we return. That's the high level. A little more detail here. And let's kind of drill. The search function is what we'd want for the search, and the sort function for the add. The search function is going to give us a negative, 0, or positive. And the two inputs to the search function are the key passed in for the search and the given data at a node. You know, if we're at this node, it'd be a 50. The given data would be a 20 at this node. So that would be the comparison. And it's going to give us, again, a negative, 0, or positive. So let's go a little bit more into detail. So here's the search for the key, and we're just going to pass it to our root. We're going to pass along the search function, so I can use that. All right, now here with the node. This is where the bread and butter is. Here with the node object. The node is going to have a search method. It is going to do the comparison using the search function. Just simply ask the search function to do its thing. And if that comparison is equal to 0, that means we have that match. Remember up there that it's going to be 0 for a match, or negative or positive for less, equal, or greater. So it's 0, so we return the data. We have the match. Otherwise, we continue on. So if the comparison is less than 0, then we do a search to the left. Otherwise, we do a search to the right. And I should say, probably here, not probably, we definitely want to actually return there and here also. Those should be return values. Okay, so now search left. So if we don't have a left, we can't search, right? If left is null, we can't do it, so we return null. We didn't find a match. Otherwise, we simply ask our left node to do a search, given the same parameters. So pretty nice, simple, statements. And then search right would be the same. It's a similar pattern as search left. But that's how I think of algorithm. We could think about an algorithm. There are others, that you could think of as well. But that's, and you probably have something similar to that, but that's just a little chat about it, so you can bounce ideas. The add algorithm, again, I'll just mention real quickly again, would be very similar to the search, except, we're not, in that case, the parameters are a little bit different, and we would be using not the search function, but the sort function, but it's the same pattern. We'd be looking in, except when we get to the point where we find the end point, wherever that might be, we don't return it. We actually then insert the new data. So that's a little bit on the algorithm, a little chat, and we'll talk to you later.